I want you to picture something with me for a second.
Oh.
You're standing at a harbor, maybe it's Rotterdam or Shanghai, or even just a busy ferry terminal, and you look up, and just blocking out the sun is this wall of steel. It's a container ship, maybe a super tanker. It is, I mean, it's essentially a skyscraper lying on its side.
It's a massive visualization.
It is massive. And you realize this thing weighs, what, 100,000 tons? Maybe even more. And it's carrying millions and millions of dollars of goods.
Right.
And then you look down at the water, and it's just sitting there. It's floating. And not only is it floating, but like next week, it's going to go through a hurricane in the middle of the Pacific, get battered by 50-foot waves, and just keep going.
It really is one of those things that when you stop and actually think about it, it seems almost impossible. It's a staggering feat of engineering.
Exactly. I had this moment of just how do we build these things? Who decides that this specific shape will survive a storm? So I started digging, and I thought we were going to talk about shipbuilding, welding and sparks.
Physical stuff.
Yeah. But it turns out we're talking about something much more specific and honestly, much more intellectual. We are talking about naval architecture.
And I'm so glad we are making that distinction right out of the gate.
Yeah.
Because while they are absolutely related, they are definitely not the same thing.
Yeah, let's clear that up immediately. Because I think I've probably used naval architect and shipbuilder interchangeably my whole life.
Oh, most people do.
Yeah.
But think of it this way. Naval architecture is the engineering discipline. It's the brain. It's the whole design process.
Okay.
It pulls in mechanical engineering, electrical, electronic software, and crucially, safety engineering.
So the naval architect is the one staring at the blank page or, the blank computer screen, figuring out if a thing will actually work in the first place.
Precisely. They are the architects in the truest sense of the word. Then you have shipbuilding.
Right.
That is the physical construction. That's the shipyard, the cutting of steel, the assembly, the launching, all of that.
So the brawn to the architect's brain, kind of.
In a way, yeah. And then just to add one more layer, you have marine engineering.
Oh, another one.
And that's a distinct field, too, that focuses specifically on the shipboard systems, the engines, the pumps, the piping, the guts of the machine that makes it run.
Okay, so let me see if I have this right. The naval architect designs the vessel's shape and structure. The marine engineer designs the systems inside it, and the shipbuilder actually puts it all together.
That's a really good shorthand. But the naval architect's role is really the umbrella over all of it. Their mission is, it's holistic. They are designing these massive structures to survive and operate in one of the most hostile environments on Earth, the ocean.
And when we say operate, we are not just talking about a nice cruise on a sunny day.
Oh, no. No, we're talking about everything from massive supertankers and aircraft carriers to high-speed hydrofoils and offshore oil platforms. The scale is immense, and the stakes are just incredibly high.
And the scope of their work is pretty wild, too, right? It's not just, here are the blueprints, good luck with that.
Far from it. The source material really emphasizes that naval architecture covers the entire life cycle of the vessel.
The entire thing.
The entire thing. We are talking about basic research before a single line is even drawn. Then you get into preliminary design, detailed design, construction oversight, trials.
Wait, trials? Like test driving a car?
Exactly. Sea trials. But it continues on into operation, maintenance, and even dry docking. And here is a part people forget. Conversion.
Right, like if a ship needs a new job or something.
Exactly. You might take an old single-hull tanker and convert it into a floating production storage and offloading unit, for an oil field. Or you modify a ferry to carry more cars. The naval architect has to be there to run the calculations to make sure this new ship is still safe, still stable.
So it's really cradle to grave or cradle to scrapyard.
Cradle to scrapyard, exactly. And involved in all of that is the formulation of safety regulations and damage control rules. It's a massive responsibility.
Well, let's get into the actual science of it, because the mission, as you put it, is surviving the ocean. And step one of surviving the ocean is, well, don't sink.
The science of staying afloat.
This is what the experts call hydrostatics.
Correct. Hydrostatics deals with the conditions the vessel is subjected to while it is at rest, in still water.
Okay, so we haven't turned the engine on. We're just sitting there in the harbor. How does a hunk of steel weighing thousands and thousands of tons actually stay up?
It all comes back to a fundamental principle that, many of us learned in school, but perhaps haven't applied to a 100,000-ton vessel. And that's buoyancy.
The old Archimedes principle.
The very same.
Yeah.
The rule is absolute. The buoyancy force, that's the force pushing up, must equal the weight of the body.
Okay, let's break that down. Weight of the body. That's the ship, the cargo, the crew, the fuel.
Everything.
Yeah.
Absolutely everything. Gravity is pulling all of that mass down.
Right.
To stop it from going straight to the bottom of the ocean, you need an opposing force pushing up.
Yeah.
That is buoyancy. And the law states that the mass of the body equals the mass of the water displaced.
Displaced meaning pushed out of the way.
Exactly. So if your ship weighs 50,000 tons, you have to design a whole shape that, when you put it in the water, pushes aside exactly 50,000 tons of water. When you push that water away, the water pushes back. That's your upward force.
So it's a perfect balancing act. Gravity pulling down, water pushing up.
We call it equilibrium.
Which sounds very peaceful, very zen.
It sounds peaceful, doesn't it? But in naval architecture, equilibrium is a constant battle. You have gravity acting downwards through a single point, the center of gravity.
Okay.
And you have hydrostatic pressure buoyancy acting upwards through the center of buoyancy. For the body to remain at equilibrium, these forces must be of the same magnitude.
And here's the kicker mentioned in the notes. They have to be in the same line of motion.
That is the critical part. Absolutely critical. Imagine a vertical line. Gravity pushes down along that line, buoyancy pushes up along that same line. The ship sits perfectly still.
But the ocean doesn't do still.
No, it does not.
Yeah.
And this leads us to the real complexity of ship motion. Because as soon as a wave hits, or the wind blows, or you drive a forklift to the other side of the deck,
Those lines unalign.
they're no longer aligned. And the ship moves.
It moves, and understanding how it moves is probably the most important part of the job.
It really is.
This was a huge aha moment for me in the research. Because if you ask a regular person how a boat moves, they'd probably say it goes forward and it, rocks a bit.
Right.
But naval architects break it down into something called the 6 degrees of freedom.
It's the standard framework for analyzing motion in a fluid. Any floating body has 6 ways it can move. And we divide them into 2 categories: translation and rotation.
Okay, let's break these down because I think visualizing this really helps you understand why designing these things is so damn hard. Let's start with translation. This is moving along a line, right? No spinning.
Correct. Shifting position. The first one is surge.
Surge. That sounds like moving forward.
It is. It's movement along the longitudinal axis, so fore and aft.
Yeah.
The ship speeding up, slowing down, or being pushed backward by a wave. That is surge.
Okay, got it. Next up.
Sway. This is transverse movement, side to side.
Like sliding sideways.
Exactly like sliding sideways. Imagine a giant hand pushing the ship from the side, and the whole vessel just slides laterally across the water without turning. That is sway.
Okay, and the third translation.
Heave. This is just vertical movement. The entire ship lifting straight up and then dropping straight down.
Okay, so surge is forward and back, sway is side to side, heave is up and down. Those are the slides.
Right.
Now we get to the rotations. This is the stuff that makes people seasick.
Indeed. These are movements around an axis. First you have yaw. This is spinning around a vertical axis. So imagine you are looking at the ship from a helicopter. If the nose of the ship twists to the left or right,
Yeah.
that is yaw.
So, steering, when you turn the rudder.
Steering causes yaw, yes. But waves can also cause involuntary yaw, twisting the ship off its course.
Okay, what's next?
Pitch, or sometimes people call it trim. This is rotation about the transverse, or side-to-side axis.
So an axis running through the middle of the ship from port to starboard?
Exactly. So the ship rotates around that, the bow goes up, the stern goes down, then the bow slams down and the stern comes up.
That's the classic riding the waves motion, tipping forward and back.
That's the one. And finally, the most critical one for stability,
Roll.
or sometimes called heel.
Roll.
Rotation about the fore and aft axis, the ship tipping side to side.
Okay, so we have 6 different movements happening, potentially all at the same time. Surge, sway, heave, yaw, pitch, roll.
And that is where the danger lies, because
Yeah.
these movements interact in really complex ways. And this brings us back to that concept of stability. Stability isn't just sitting flat. It is the ability of the vessel to restore itself to an upright position after being inclined by wind or sea or shifting cargo.
It's the ability to bounce back.
Yes. If a gust of wind pushes the ship over into a roll, stability is the force that pushes it back up. If the ship doesn't have enough stability, it rolls over and it doesn't come back. That's a capsize.
There's a very specific, very technical danger mentioned in the source material that I want to unpack. It involves a relationship between 2 of those movements we just talked about, roll and heave.
Ah, yes. This is a fascinating and, frankly, terrifying phenomenon. It's all about resonance.
A resonance, like a singer hitting a note and shattering a wine glass.
Exactly the same principle. Every object has a natural period, a sort of timing at which it wants to vibrate or oscillate. Ships have a natural roll period.
The time it takes to rock left, then right, and then back to the center.
You got it. The source highlights a specific danger zone. If the period of oscillations in roll is 2 times that of the period of oscillations in heave, you have a serious problem.
Wait, let me get that straight. If the side-to-side rolling takes twice as long as the up and down heaving,
Yeah.
that's a disaster.
It can be. It creates a feedback loop that we call parametric rolling.
Right.
The energy from the ship just bobbing up and down on the waves, gets transferred into the roll. It starts to amplify the rolling motion.
So even if the waves aren't getting any bigger, the ship starts rolling more and more violently.
Exactly. It feeds on itself. And it can happen very, very quickly. The ship can start rolling to extreme angles, damaging cargo, tossing the crew around, or in the absolute worst case scenario, capsizing.
That is terrifying. It's like the ocean finds the ship's weak spot, its secret rhythm, and just uses it against it.
And the naval architect's job is to ensure that doesn't happen. They have to calculate the center of gravity and the longitudinal metacenter to basically tune the ship so that this resonance doesn't occur in typical sea conditions.
You mentioned the metacenter. That term popped up in the notes. It sounds super sci-fi. The longitudinal metacenter.
It sounds complex, but it's really just a point in space derived from the ship's geometry. It's a point that determines stability.
Okay, so how does it work?
Well, stability depends on the distance between the center of gravity, where the weight acts down, and this metacenter. The notes describe it as depending on the distance set equally apart from both the aft and forward section of the ship. Basically, it's the pivot point for the righting forces. If your center of gravity is too high relative to the metacenter, you're top-heavy. You become unstable. You flip.
So you always want a really low center of gravity.
Generally, yes.
Yeah.
But if it's too low, the ship becomes what we call stiff. It snaps back upright so fast and so violently that it's dangerous. It's a constant trade-off.
So we've got the ship floating. We've hopefully kept it from flipping over due to some rogue resonance. That's all hydrostatics.
Right.
But ships aren't meant to just sit there. They have to move.
And that brings us to our next big topic, the science of moving, or hydrodynamics.
Hydrostatics is water at rest. Hydrodynamics is water in motion.
Precisely. This covers the flow of water around the hull, the bow, the stern, and over bodies like propeller blades and rudders. It's all about how the ship and the water interact when there's movement.
So it's basically the study of resistance, right? The water doesn't want the ship to move through it.
It resists. You have friction of the water against the hull. You have the energy that's lost, just creating the waves that trail behind the ship. The naval architect has to design a shape that slips through the water with the least amount of resistance possible.
Because that dictates how big your engine has to be.
Resistance and propulsion are 2 sides of the same coin. Once you know the resistance at a certain speed, you can calculate the propulsion power needed to overcome it.
The source lists a few ways to move a ship. We're all familiar with propellers, obviously.
Propellers are still the standard, yeah. But you also have thrusters for maneuvering, especially for holding a position, and water jets for high-speed vessels.
And I saw that even sails are mentioned.
Yes, wind-assisted propulsion is making a comeback, actually, for efficiency. And of course, the power source varies. You've got internal combustion engines as the workhorses, but you have nuclear power for naval vessels and icebreakers. Solar is starting to emerge for smaller things.
And tied into all of that is controllability.
Maneuvering. It's not enough to just go fast in a straight line. You need to be able to turn, to stop, and to maintain position.
Like that dynamic positioning on those oil rigs, where they just stay in one spot.
Exactly. Keeping a vessel perfectly still while waves and wind are trying to push it around requires this incredibly complex interaction between sensors, computers, and multiple thrusters. That is all hydrodynamics.
Okay, let's talk about the physical stuff, the bones of the ship. We've talked about all these invisible forces, but what is the ship actually made of?
This is the structural integrity part of the discipline, and it's a big one.
I was kind of surprised to see that despite all the carbon fiber and fancy materials we have today, the answer is still overwhelmingly steel.
Steel is still the king. It's strong, it's relatively cheap, and crucially, we understand it very, very well. For the hull of any major commercial vessel, it is almost always going to be steel.
The source does mention aluminum, though.
Right, but usually for the superstructure, the house part that sits above the main deck, it's lighter, so it helps keep that center of gravity down, which helps with stability.
And smaller boats might use glass-reinforced plastics, Fiberglass.
For sure. But for the big beasts, it's steel plates. But here is the thing. You can't just weld a bunch of flat steel sheets together and hope it floats.
It would be floppy, right? Like a big baking sheet.
It would buckle under its own weight before it even hit the water. So they use a system of construction involving grillages.
Grillages. I love that word. It sounds like something you cook on in the summer.
You could visualize a waffle iron or just a grid.
Yeah.
You have the flat steel plate, but welded to it are stiffeners. You have ribs running one way and beams running the other way.
So the plate is supported on all four edges by these stiffeners.
Exactly. These rectangular panels, these grillages, are what make up the hull, the deck, and the bulkheads, which are the internal walls. It turns a floppy sheet of metal into an incredibly rigid structural component.
But even with these grillages, the ship faces a massive structural threat. The source calls it longitudinal bending.
This is the big one for long ships. Imagine the ship is a long beam, or like a ruler held between your hands. Now imagine a wave that is about the same length as the ship.
Okay.
If the crest of the wave is right in the middle of the ship, the bow and the stern are kind of hanging in the air, unsupported.
So gravity is pulling the ends down. The ship wants to frown.
We call that hogging. Now imagine the opposite. The trough of the wave is in the middle. So the bow is on one crest, the stern is on another crest. The middle is unsupported.
So the middle wants to sag down.
Exactly, sagging. These forces are immense. We are talking about tens of thousands of tons trying to bend and snap the ship in half over and over again.
This leads us to a really cool piece of engineering history that was mentioned in the outline, the Isherwood system.
Yes. This is a classic example of how engineering evolves to solve a huge problem.
So walk us through the evolution here. How did they used to keep ships from snapping?
Well, way back in the day, think of the SS Great Eastern in the 1800s. They used longitudinal stiffening. The main support beams ran the length of the ship from front to back.
That makes sense. I mean, if you don't want a ruler to snap, you reinforce it lengthwise.
It worked, but it was really difficult to build, very labor-intensive. So as the industry scaled up, they switched to transverse framing.
The ribs ran side to side?
Like the ribs in your chest, yeah. It was just easier to assemble. And for smaller ships, it was perfectly fine. But then in the early 20th century, oil tankers started getting bigger and longer, much longer.
And the transverse frames just couldn't handle the bending forces anymore.
They were struggling. The ships were getting really heavy and inefficient because you needed so much steel. And then along comes Sir Joseph Isherwood. He basically reintroduced the longitudinal system, but in a much smarter, more optimized way.
How so? What did he change?
He realized you didn't need those heavy longitudinal beams everywhere. You mostly needed them on the deck and on the bottom of the hull. The flanges of the beam, if you're thinking of the ship as an I-beam, that's where the stress is highest during hogging and sagging.
So he just stiffened the top and bottom with these long beams?
Yes, these strong longitudinal members. And because the deck and bottom were now so strong, he could space the heavy transverse ribs much, much further apart. The source mentions spacing them 3 to 4 meters apart.
That's a huge gap compared to the old way.
It is, but it worked. It kind of displaced the force that the bulkheads would have provided. It created a lighter, stronger ship that was easier to build. It completely revolutionized tanker design.
It's cool how sometimes the new innovation is just a smarter version of the old way.
Engineering is often cyclic like that. You find new ways to apply old principles.
Speaking of structure, there was one detail in the construction segment that I found absolutely fascinating. It was about crash science.
The crashworthiness of the vessel, yeah.
Right. When I think of safety in a collision, I usually think armor. You know, make it impenetrable. If another ship hits me, I want my ship to be a brick wall.
That is the intuitive thought. But in physics, being a pure brick wall is often a really bad idea.
Why is that?
Because if two massive objects collide and neither of them gives at all, the energy has to go somewhere. It goes into shock. It creates instantaneous catastrophic failure. It could shatter the structure, break the keel, or rupture all the tanks at once.
Yeah, so what's the strategy then, if not a brick wall?
Elasticity. The source mentions that materials are chosen for their elastic properties.
You want the ship to be, what, squishy?
In a controlled way, yes. You want the structure to absorb the energy of the collision. You want it to deform, to dent, to crumple, but just locally.
Like the crumple zone on a car.
Exactly like that. But the goal, as it was stated in the source, is for the struck ship to absorb energy and deflect it, causing both ships to rebound.
Rebound. That's such a dynamic image. You actually want them to bounce off each other.
You want to convert that kinetic energy of the collision into deformation energy and then into potential energy that actually pushes the ships apart. It prevents the deep, penetrating damage that sinks ships.
So the naval architect is essentially engineering a skyscraper that is also designed to bounce if it gets hit.
That is the level of complexity we are dealing with. It's wild.
This feels like the perfect transition to our third segment. We've talked about the math, the physics, the steel, but the source material has this section titled Art versus Science.
This is my favorite part of the discipline because it acknowledges something very, very important. We haven't figured it all out yet. Not by a long shot.
It starts with the history. Traditionally, naval architecture wasn't a science at all. It was a craft.
It was. You didn't have computers or calculators. You didn't have fluid dynamics simulations. You had a master shipbuilder who would carve a half model out of a block of wood.
And how did they decide if the shape was any good?
By eye and by feel. They used subjective terms. They would look at the curves of the hull and say the shape was ungainly or full or fine.
Fine. That doesn't sound very scientific. Yeah, that whole shape looks fine to me.
It's funny, but in this context, fine meant something very specific. It meant the lines of the ship were fair.
Fair. That's the key word here, isn't it?
It is. A fair shape meant there were smooth transitions, no abrupt changes in curvature. It just looked, It looked like it would flow smoothly through the water.
And the crazy thing is, they were usually right.
The human eye is incredibly good at detecting geometric flow and fairness of a curve. Those fair shapes were often very efficient.
But now, of course, we have moved from craft to computation.
We have. We use CFD, that's computational fluid dynamics. We create digital twins of the ships in software. We use programs like Aveva, Trabon, or K3D. We can model the ship in a virtual ocean and see how it behaves.
So surely the art is dead then. We just let the computer figure it out.
You would think so. But the source makes a fascinating point. It says that the analytical tools for ships are actually less evolved than those for aircraft or spacecraft.
I stopped when I read that. I mean, we can fly a drone on Mars. We can land a rocket on a tiny barge in the middle of the ocean. But we can't perfectly model a boat. Why?
It comes down to the environment. The source cites the paucity of data on the marine environment.
Paucity meaning lack of.
A severe lack of. Think about space. It's a vacuum, it's empty, it's predictable. Think about the air, it's a fluid, but it's relatively light and fairly consistent. Now think about the ocean surface during a storm.
There's chaos.
Total chaos. You have wind, you have waves coming from different directions, you have currents. And the interaction between those random waves and the moving ship is incredibly fiendishly difficult to predict accurately.
So the input data, the sea itself, is the problem. We can't model it perfectly.
Exactly. Predicting the ship's response in a random sea is infinitely more complex than predicting drag in a wind tunnel. Because of that gap, that uncertainty in the data, the science can only take you so far.
So you still need the naval architect to step in and say, the computer says this is okay, but it doesn't look fair.
Exactly. The art of determining what is right still exists. That intuition, that experience, it fills the gap that the science hasn't closed yet.
That brings us to the role of the naval architect today. It's clearly not just some guys sketching lines on paper.
No, not at all. It is a cooperative effort. The naval architect is a team leader, an integrator.
The managerial challenge.
Yes. They are managing a team of specialists. You've got structural engineers, hydrodynamicists, interior designers, marine engineers, weapons systems engineers on a warship. And they have to integrate all of that into one coherent design.
And they are juggling these huge conflicting demands. The source lists 4 big ones: safe, economic, environmentally sound, and seaworthy.
And those are almost always in direct conflict with each other.
Give me an example of that conflict.
Okay, well, take safety versus economics. To make a ship safer, you might add more steel, more watertight bulkheads, more backup systems.
Which makes it heavier and more expensive to build.
Heavier means it burns more fuel to move. That hurts the economics. And burning more fuel hurts the environmental goal.
So you fix one thing and you kind of break 2 others.
Exactly. Or seaworthiness versus comfort. A ship that is very, very stable, which is good for safety, might be very stiff and snap back violently in waves. That makes the passengers sick and can break the cargo.
So the naval architect is the diplomat in the middle of all this.
They are the integrator. They have to find the optimal compromise that makes the product fit for purpose. They have to look at the owner, the regulators, and the ocean itself and find the one design that satisfies them all as best as possible.
And they're doing this for an absolutely incredible variety of vessels.
The diversity is stunning. Merchant ships, ferries, warships, submarines, hovercraft, giant offshore platforms.
It's everything that touches the water, really.
It is. And as we said right at the beginning, some of these are the largest movable objects that humans have ever built.
So let's bring it all together. We've gone deep on the physics, the history, the art. But for the listener who is just, commuting to work, why should they care about naval architecture?
I think it fundamentally changes your perspective on the world. I mean, we live on a blue planet. 70% of the surface is water. And almost everything you own, your car, your phone, your clothes, it almost certainly spent time on a ship.
And that ship didn't just happen.
No.
Yeah.
It is the result of a massive intellectual effort. It is the integration of massive structural engineering with the wild fluid dynamics of an unpredictable ocean.
It's calculating the heave and the surge. It's trusting the grillages to hold together.
It's knowing that even when the waves are crashing and the wind is howling, someone, somewhere, ran the numbers to ensure that the buoyancy force would win against gravity every single time.
And I think I'll never look at a boat the same way without thinking about that art.
A fair shape.
Yeah. The idea that even with all our supercomputers and nuclear engines, there is still that human element, that ghost of the old shipbuilders looking at the hull and saying, yes, that is fair. That looks right.
It connects us to thousands of years of human history. It's a beautiful thought, really.
So the next time you see a ship on the horizon, don't just see a metal box. Think about the equilibrium, think about the elasticity, and think about the naval architect who had to be both an artist and a scientist to design it to survive the chaos.
Couldn't have said it better myself.
Thanks for taking this deep dive with us.
It was a pleasure.
We'll see you on the next one.